Swayam Prabha. Digital India. Educated India.
Spectroscopy is very important in science, engineering and technology, everywhere. Okay. In science, whatever we do, we make molecules, we do a lot of things, we make powders, we make films and all that. You need to know what that is, right? So, to see that, you need to have a spectroscopy technique. Suppose I give you sugar. How will you know that it is sugar? I will not tell you anything. I will just say, okay, some sugar sand, I will mix it and give it to you. So you start doing some scientific thinking. Okay, there is crystal, the small particles look different. Maybe put here or put it in water and see one will dissolve, etc. Right? Similarly, in air you have so many molecules. How do we know there are so many molecules? We don't see anything here. You are breathing. These invisible stuff, what we are breathing, what we are, you do like this, you feel cold, right? Why? Something is happening, something is interacting with your skin, right? You feel that. Something is there, so you need to worry about what that is, right? That's where the scientific inquiry comes. When scientific inquiry comes, okay, so how do I interact, how do I actually see them, or how do I measure their properties, see their properties, etc. Right? So that's where spectroscopy comes in. Spectroscopy is basically light interaction with matter. So if the light is falling on some molecules, the molecules respond to that. Okay. So molecules have variety of things. Vibrational, rotational, translational, electronic excitations, nuclear excitations, all these are possible in the molecules or matter. It can be molecules, it can be powders, it can be anything. So this is all about gaseous state and solid state and so on and so forth. But there is something very interesting. God created solids, but devil created surfaces. Devil created surfaces. You take anything, there is a surface. See the wall, there is a surface. You see you are sitting at the table, there is a surface. Skin, there is a surface. Floor, there is a surface. Without surface, somewhere it has to end. There is a surface there. Right? You have a surface on the road. Why surface of the road is important? Okay. If there is no friction, so you lift your car about 2 centimeters up and accelerate it. You will be there only. Right? So the friction is important. So there is a surface and interface. So these are very important. Surface and interfaces are very, very important. Right? You have a skin here. So with a lot of moisture outside, humidity is very high. You start sweating. Otherwise, what happens? The water that comes out, it starts evaporating. You feel better. Otherwise, you feel miserable. Feel like taking bath. Right? So similarly, if you take solids, the solid, there is a gas and solid. This is an interface. This interface is not so easy to understand. The molecules are hitting the surface. Some of them may be, absorption. They may absorb. They may react. Iron, if you take, iron will pick up oxygen from this one and then give you a iron oxide film. It can be thin, it can be thick. If you leave it for a longer time, it can be thick. Now, I want to understand what is happening there at the surface. A few angstroms. Right? That's where you need a spectroscopy. This is a spectroscopy which is specifically meant for that. What I am going to teach you. This spectroscopy is based on photo emission. You have studied photo emission, right? Photo emission you have studied? Suppose you shine light, electrons come out. Photoelectric effect. Photoelectric effect, all of you. That photoelectric effect is converted to spectroscopy. Okay? Now, you should also know there is something called, this is called photoelectron spectroscopy, the introduction to photoelectron spectroscopy. This is this book is written by Professor P.K. Ghosh, very interesting, 1983. He is the first person who tried to build a photoelectron spectrometer in India. Why it should be import everything? He tried to build, he built some spectrometers. He's still alive, he's there. He's an old man, but he's still somewhere living in Calcutta. Very great teacher. Okay. So, now I am going to tell you a few things quickly. So, here this XPS technique is based on Einstein's idea about the photoelectric effect developed in 1905. Einstein explained photoelectric effect. He said kinetic energy plus binding energy is equal to photon energy, right? And then the concept of photons was used to describe the ejection of electrons from surface when photons are impinged upon it. You have photons, you just shine these photons on a surface of some metal, electrons come out, right? Particularly if you take cesium metal it is easy to get electrons out because the work function is very, very small. About 2 eV UV light if you shine, you can get electrons. Okay. Now, but from 1905 to all the way up to 1960s, it took nearly 55 to 60 years to develop this concept into a spectroscopy technique called X-ray photoelectron spectroscopy. X-ray photoelectron, because that period there was a lot of electronics, vacuum systems have to be developed, the technology was not available. So, slowly it took so much of time to develop that. Finally, they could build the spectrometer somewhere around 1960s. 1960s, that year I was born. None of you are there. Right? So, in 1981, for doing this one, Sigmund, Kai Sigmund, in 1981, he got Nobel Prize in physics. Nobel Prize in physics. Okay? Now, what is important here is, this is your all, this one. You have a light of particular frequency. You shine that light. If the light frequency is crosses critical frequency, is beyond that, then you start getting electrons out. These are photoelectrons. This is a linear relation. H nu is equal to phi. Phi is the work function. What is the work function? Okay. So, the work function is something which, I mean, qualitatively I will explain to you. Suppose I have a surface, I try to remove electron. So, the solid will not allow that. You remove electron, there is a positive charge, it will just pull it back, right? You apply enough energy, take it out, after some time that influence will come to 0, right? So, it is free, electron is free. So, that energy which is required, you can call it as work function, okay, right? So, if that work function, if H nu is that work function, that is something somewhere here. I mean, if H nu is more than that, then you start going this way, you get photoelectrons. Photoelectrons will have kinetic energy. Now, here electrons we are treating as particles. Electrons can be treated as particles and waves, right? All of you know that, right? Yeah. So, now, if the electrons are removed from the solid, then the H nu should have this much of energy plus phi. This is the kinetic energy by which the electrons come out. Okay, that is solid. If it is a gas phase molecule, also you can remove electrons. Those electrons basically ionization. You need to have supply that much of energy to ionize the gas molecule. So, you remove the electron, okay, and it will come out with some kinetic energy. Okay, all right. This is a very simple one. Okay. Now, this is kind of a cartoon where you have a UV light falling on cesium metal, electrons are coming out. Electrons are coming out. Okay. So, this thing simple, you have a sample, we deal with
Sir, this equation is to take out one electron, right? Now, if I want to take out more than one electron,
Yeah, you apply everywhere. Or any electron, you apply the same equation.
sir, but according to equation, the energy after removing the electron goes into giving the kinetic energy to the electron. So, when I want to take another electron, I have to supply energy again.
Yeah, sure.
So, after I take out, should I apply energy? If I put it in the
Okay. So you shine the light, you get electron out, you will have many electrons coming out, right? And the surface gets charged. But there are electron supply already from behind. It's a very fast process. So you have many electrons coming out, different electrons coming out. But it gets neutralized by the electrons coming from within the system. Okay? Otherwise what happens? You remove electrons, it will become charged. So you have to nullify that charge. So it automatically does, because it says metallic samples, etc. If it is a insulator, of course it will get charged. So they do additionally, they add, sprinkle some electrons on the surface. There is a electron gun they use to neutralize the charge. Okay, all right. So simply, so you normally this kind of experiment, people use X-rays. Ultraviolet light radiation is also used. X-rays are also X-rays, aluminum K alpha, magnesium K alpha. Those are all X-ray tubes are available now. There are 2-3 XPS machines in IIT Madras. Okay, maybe you can go and have a look at it. With the coordinator here. Yeah, no. Okay, I'll show you in the picture at least. I'll show you the photo. So you have these X-rays coming out. These X-rays have single energy. What do you call that? Monochromatic photons. Monochromatic X-ray photons. Monochromatic means energy is same, right? So that energy is something like 1486.6 or 1487 electron volts, and then you send those X-rays. So this is a sample. On the surface, they start removing electrons. So you know this energy, because that is what you are using, right? So you catch these electrons and measure their kinetic energy, right? So H nu is equal to kinetic energy plus binding energy. Forget about work function. H nu is equal to kinetic energy plus binding energy. You know kinetic energy, and then you know H nu. So binding energy you can calculate. What is this binding energy? This is the energy of the electron where sitting in a particular level. Okay, all right. So they have taught you atomic atom. In the atom we have 1s, 2s electrons, 3s, 3p, 3d, 4f electrons, right? What is the experiment? What is the proof that they have? Some quantum mechanically you say that these are all energy levels that you have. What is the experimental proof? This is the experimental proof. This is this experiment will give you the proof of electrons sitting in different levels, s orbital, p orbital, d orbital, and so on and so forth. Whatever we talk, we always look for some experimental evidence should be there, right? Even if you predict something, right? So you may not be able to prove it immediately, but at some point of time, a experiment can be designed. Experiment can be designed to prove that. So now here these electrons are coming out. You measure the kinetic energy of these electrons, and this this is about 10 nanometers. This width is about 10 nanometers. So X-rays go and penetrate up, let us say, little more than 10 nanometers, but the electrons which are coming out in about 10 nanometers, that means about 100 angstroms. Those are the electrons which come out of the surface without losing their energy anywhere. Okay, what they get ionized and then they come out. So that they remember from where they are coming, right? So if you analyze their kinetic energy, then you can find out the binding energy of those electrons where they are coming from. Okay, all right. So this is only about 10 angstroms, 10 nanometers here. It will not say what is there below. Okay, all right. 10 angstroms is 10 nanometers is 100 angstroms. How much is that 100 angstroms? How do you measure 100 angstroms? Can you imagine 100 angstroms would be how much? But from here to here? Huh? This much? Can you tell me? In some way you have to measure, find out a scale. 100 nanometer, 100 angstroms. What is the diameter of hydrogen atom? Huh? 0.5 angstroms, right? In 100 angstroms, how many hydrogen atoms can be arranged? 200. So 200 hydrogen atoms. That is the depth that electrons will come out. Of course, even below that also, but these are the electrons which can be analyzed. Huh? That is Bohr model. If you read Bohr model, you want to calculate, you will get that 0.5 angstroms. Huh? Yeah, that is the one of the evidence, right? How do you experimentally verify? Yeah, so hydrogen, you can use spectroscopy methods, find out the bond distance, right? From bond distance, one can estimate all that. Okay, that is possible. Okay, and there are other methods also. There are a lot of other methods, to find out the atomic radii, ionic radii, etc. There are other methods. Okay, now, so this is basically the experiment. So what you have here is X-rays go in, electrons come out. X-rays go into the solid, electrons come out. This is solid surface I am talking about. Solid surface. But same thing can happen even gas molecules also. Even liquids can be analyzed. X-ray photoelectron spectroscopy can be carried out on liquids also, but that is a little more difficult. Okay, people have attempted that. Now, work function I was talking about, there are so many metallic systems here. Work function is there not only for metallic systems, it can be there for semiconductors, it can be there for solids, oxides, insulators, and so on and so forth, right? So, the lowest work function is in this table is cesium 2.1 electron volt, which is equivalent to something like UV. Ultraviolet radiation has similar energy. So, the moment you take some UV and then shine it, you get electrons out. Okay, all right. And other metals, it may have a higher values, about 4.4 electron volts, gold 5 electron volts, and so on and so forth. Okay, all right. Work functions are high. Some of those cases. Why cesium has low work function? It is easy to remove that S electron. It will be very stable. It becomes very stable. It's easy to, all alkali metals, it's easy to remove electrons, 1s electrons. Huh? Work function of? Francium is, is not an element to deal with regularly because it's a radioactive kind of thing. So we just stop at cesium, or that is for our purpose we can stop at it. Of course, yes, francium can be analyzed. Why not? Francium can be analyzed. But if you have a compound, yes, you can analyze that also. That is possible. Okay. Now, so just to give you a gist of it, irradiate the sample, hitting the core electrons of the atoms using X-rays. X-rays, when you use, these X-rays can go to core electrons. You have valence electrons and core electrons. For example, in cesium, what you are removing is a valence electron, but there is a core electron there. So for that you have to use higher energy X-rays. Otherwise, UV is sufficient. UV also will remove electrons from the valence levels, right? So here, so you hit the core electrons, X-rays penetrate the sample to a depth of order of micrometer, right? But then you analyze electrons only coming out from the about 100 angstroms, because the other electrons which are coming from below, Suppose you have a surface here, you can actually ionize the electrons, let us say up to 1 micron. But then the electrons which are coming here, they have to pass through the sample and then come out. While doing that, they lose energy. So they have lost their memory from where they are coming. So that becomes a background kind of noise. But electrons up to 100 angstrom roughly, they can actually come out without losing energy. They remember the memory from where they are coming. So you catch that kinetic energy of that electron, so you can say which orbital or from which orbital it is actually coming out. This is true for solids. Okay, all right, very good. Now, so useful signal is obtained only from a depth of about 10 to 100 angstroms of the surface. I am talking about solid surfaces. So X-ray sources produce photons with certain energies. For example, magnesium K alpha has 1253.6 electron volt, aluminum K alpha has 1486.6 electron volts. The moment you say magnesium K alpha, aluminum K alpha in the X-ray spectrometer, energy is fixed, monochromatic photons. Monochromatic photons. Okay. And then normally sample will be radiated with photons of single energy. That is this one, the single energy. This is known as monoenergetic X-ray beam. Monoenergetic X-ray beam. Yeah. That is X-ray notation. See, when you are actually taking in aluminum, for example, or magnesium, in the tube, there will be an anode. In this anode, they coat aluminum here, thin aluminum film, and then magnesium film, right? And then they pass electrons, about 3 kilo electrons they hit on that. That releases the X-rays. But these X-rays are basically the transitions, from K, L, M shells. That is SPD. In X-ray notation, there is K, L, M shells. So those transitions are named after this one. Okay. For that, if you wanted to know more about this, you have to go to the X-ray spectroscopy. X-ray spectroscopy, that is a different story altogether. Okay, that comes from there. All right. Okay, now come to atom. Like we have an atom here, and this one is nucleus, and you have electron here. Let us say there is one electron here, and there are electrons in this. Right? Electrons look like that. Electrons go around on a circle. Why? How do we know electron is in 1s orbital? Can you catch the electron? It's basically a charge density cloud, right? Okay, we are only representing just to schematically we are doing it, but this is not actually correct. We just say there is a nucleus, there is a core electron. Only for our understanding we draw that. Don't think that electrons are going to be moving in a circle and all that. That's not correct. Okay. Now this electron, now you can have so you can have an X-ray. This X-ray can ionize up to even core electron. It can ionize this also, but it can ionize this as well. Okay, X-ray has higher energy. Then the electron comes out. Electron is free now. Okay. Now, so these are all protons, neutrons, and these are all the electrons. This is vacancy here. The electron is removed. There is a vacancy here. Okay. This electron you call it as photoelectron. This electron is called photoelectron. Yeah. They jump into that. That process is called Auger spectroscopy. Auger electron. I'll give you that. Yeah, if the electron is removed, there is nothing there. No, you call it as a hole. It's not a hole like physically. The electron is not there. Electron is not there. Yes, it can happen, but that's what I am saying. If if it is an atom, you ionize it, it just comes out. It's not going through any medium. But if you ionize the atom which is sitting in a solid, when the electron comes out, if it is coming from the deeper side, then by the time it comes out, it will hit the other electrons around and it will lose some energy, right? Okay, yeah. Now let's look at this. Now this diagram, this particular diagram. See here, let us say you have a solid. Solid is made of atoms. For example, copper substrate or any metallic surface substrate made up of metallic atoms, right? And then if you see, they will have electrons 1s, 2s, 2p, and so on and so forth. You can even take carbon, for example. So 1s, 2s, 2p, so on and so forth. You will have a lot of energy levels. And then when you go to the valence level, right, it forms a band. You are aware of that, right? It forms a band. So this is a kind of a valence band or valence levels. If it is a atom, it is a valence level. If it is a solid, it becomes a valence band. They are so close, it forms a band, right? Now you are using a photon, X-ray photon, to remove electron from the core level. So you call it as core hole. This electron comes out. That energy is analyzed. That gives you the XPS, X-ray photoemission spectroscopy. Now you can have a photon. To ionize these electrons, you don't need X-rays. You don't need very high energy. Some of them sitting here, they can't even see this, no? Oh, you have something there. Okay. So now, if you want to remove these electrons, you need only less energy, something like UV. UV light, if you shine, this can be ionized. This will come out here. This is also photoelectron, but this is ultraviolet photoelectron spectroscopy. The light that you use, that is named after that. So ultraviolet photoelectron spectroscopy. Here we are using X-ray, so you call it as X-ray photoelectron spectroscopy. Both are photoelectron spectroscopy only. Okay, all right. Now somebody asked the question, suppose you remove this electron, there is a hole here, in the sense that electron is removed from here. So immediately the atom becomes unstable. You have disturbed the natural neutrality of the atom. You have disturbed that. So the atom is very unstable now, right? So immediately, this electron, next higher level energy level electron can jump into this. In this process, that much energy is released. That's what your question. That much energy is released. That energy can come out as fluorescence. Some kind of, it will just emit out. Or that energy can be picked up by another electron which is sitting here. And that electron will come out. That is called Auger electron. Auger.
Should the Auger electron be the immediate next shell or the energy level, or it can from any?
From any.
So they will emit different rays.
Yeah. So you can even name them also. It can be this level. It can be this. Maybe it can even pick up from this level, or it can even from here also. Right?
According to the energy.
Yeah. You will have many Auger electrons, not one. Depending on the transition, you can have many Auger electrons. But one of them will be very intense. Probability is very high. Others may have small peaks. Right? Okay. All right. So you can have actually measure the energy now. Binding energy 1s is equal to h nu minus kinetic energy. For the time being, we ignore work function because work function is a nuisance actually. It's not a nuisance, some way it is also good. Work function. If you want to measure the energy of the electron, you take some reference. So with that reference, we eliminate the work function. Like you want to measure the height of the tree. You don't go and dig and find out the last end of the root, right? Do you do that? From the ground, reference, you measure it similarly, right? Okay. But if you want to do some more accurate calculation, etc., they consider that also. That is a different. We don't need it for experimental purpose. So you have this. So this expression. This is what Einstein gave in 1905. Einstein gave that. To convert that into a spectroscopy, it took 60 years. Right? Einstein did not use aeroplane. He did not know aeroplane. He did not know cell phone. Poor man. Right? Did he know this? Einstein didn't know this. Einstein did not travel in the aeroplane. But he did a lot of things which we are using it now. You can't ignore him. He said so many things, interesting things that they are all true. Right? So this Auger electron, if you can analyze that, you can have another spectroscopy called Auger spectroscopy. Auger spectroscopy. Why you guys are looking at each other and smiling? You are hungry? Is it interesting or boring? Some? Okay. Yeah, that's okay. Sounds come, Universe is noisy. Universe is not silent. Right? You go to the upper sky, you see all kinds of noises there. All right. So this is the kind of a picture of what photoemission spectroscopy is all about, and a small thing is Auger electron spectroscopy. Now, that normally in the lab we use you have X-ray tubes, and then you have helium lamps which actually give you these photons, and which we use that, okay, in the lab. Now, so core electrons are local, close to the nucleus, and have binding energies characteristic of their particular element. What does it mean? It means that if you have a solid, if you analyze valence electrons are not mobile, conductive. They don't belong to a particular nucleus. Correct? Suppose you take copper. Copper has a band, no? The valence electrons form a band. So they don't stick to one particular nucleus. They just move around in the solid. It's like a sea of electrons where the copper atoms are sitting, copper nuclei are sitting. But when you go to core, that electron sticks to the particular nucleus. Right? So that is the reason why you need to analyze core electrons to find out the binding energy of that particular electron. Okay, so that's the basically. So that means it's a characteristic of their particular element. So since they are confined to a particular nucleus, if you analyze their kinetic energy, then you will be able to find out what? Find out what? Which atom it is coming from. Which means you can actually find out what are the elements present in the sample. Right? Okay, you don't see them, but you can analyze them. Isn't it beautiful? Right. I think I'll skip this. So this is again a cartoon kind of thing. You have a nucleus, 1s, 2s, 2p, X-ray photons come and remove that, right? So people call it as X-ray photoelectron spectroscopy. Those days, some 30 years back when I was a student, people used to call it as ESCA, electron spectroscopy for chemical analysis. But now people have stopped using that. But then ultraviolet photoelectron spectroscopy, where ultraviolet radiation is used. In general, some people use it as simply photoemission spectroscopy. All are essentially same. Okay. So what are the steps involved in this photoemission? Absorption and ionization of the element. Okay. All right. And then response of the atom and creation of photoelectron. This is initial state, this is the final state, and then transport of electron to surface and escape into the outside the surface. Now, if you want to do this experiment, can we do it under atmospheric conditions? You cannot do it under atmospheric conditions because the electron will go and hit all the molecules. It will lose its energy. You have to Huh? Sorry?
Isolated.
So what you need to have is vacuum. So what is the pressure that we have around us acting on our body? 1 atmosphere. Now you reduce that one to, let us say 10 to the power of torr. So 1 atmosphere torr. So you pump out the gas, create a vacuum which is of the order of 10 to the power of minus 9 torr. 10 to the power of minus 9 torr. Under those conditions, the photoelectron which is coming out will have a sufficient mean free path to go from the sample to the detector. Now this is photoelectron is running around. How do you catch it? That is another question, right? Isn't it? You can't see it. Can you see it? But you have to catch it and then measure its kinetic energy. Now there you need to have the technology, engineering technology, etc. All those things are important, right? Now photon absorption is very fast. It happens in 10 to the power of minus 15 to minus 16 seconds. Okay. No photo emission. This is some summary. The no photo emission for h nu is less than work function, that we know now. Now no photo emission, kinetic energy as photoelectron increases as binding energy decreases. Is that correct? How? Tell me how it is. Those who are sitting here, they are not.
Minus 5 and as 5
Exactly. H nu is fixed. Binding energy is fixed. Binding energy cannot be changed, right? So all that you can do is H nu. If you want to change, you can change H nu, different sources, and binding energy is fixed. That is characteristic of the element. Work function is also fixed. So kinetic energy of the photoelectron increases as binding energy decreases. Are you able to understand all that? Okay, something like that. If you change this will change. Okay, all right. So that's what he said here. The kinetic energy of photoelectron increases as binding energy decreases. These two are opposite. These two are opposite because this is fixed. Okay, all right. You require monochromatic incident photon beam. That means monochromatic means all photons should have the same energy, h nu. Okay, then only you can apply this equation. Otherwise, it will not be possible. So the people pick up monochromatic photons. Each element has unique set of core levels. For example, 1s carbon 1s is different from nitrogen 1s, is different from oxygen 1s. Binding energy change because the nuclear charge is different. Binding energy is going to change. Higher the nuclear charge, higher the binding energy. All are 1s electrons only, but they are unique to that particular element. Okay, all right. So that is a fingerprint of that element. The moment you catch that electron and measure the kinetic energy, you know that this electron has this energy. So this is coming from oxygen or carbon or something else. Okay. Okay. Binding energy represents the strength of the interaction between the electron and nuclear charge. Electron can be n level L, n L, m s, quantum numbers, right? So a particular electron with a particular n value, L value, m value, s value will be there. So you ionize that, and that electron interacts with the nuclear charge. So the binding energy is related to that. All right. So binding energy of 1s electron is greater than 2s electron, is greater than 2p electron, greater than 3s electron, and so on and so forth. Is that clear? 1s electron is very close to the nucleus. No, the binding energy is very strong. Yes. Then binding energy of sodium 1s is less than magnesium 1s, is less than aluminum 1s, and so on, so forth. Right? So binding energy orbital is not affected by the isotopes. That is another important thing. You can have hydrogen, deuterium, tritium, or any other isotope, chlorine 16, 17, etc. So the isotope will not affect the binding energy. They are independent. So if you have isotopes, you will not be able to figure out here. And then how will you figure out how isotopes present in the sample? What experiment would you do? Mass spectrometry. Mass spectrometry embeds that mass is there. Isotope mass is different, normal one is different. So there mass spectrometry you can use to distinguish that, right? So that particular thing has to be studied there. No, I want to use a photo emission to study this, it is not possible. Okay, all right. Okay, let me just skip the here. So this is the nucleus, these are core electrons, these are the valence electrons. Okay. So they remove this electron by slowly when it comes out here, it is it's actually it is now away from the influence of this level. So you need that is a gives you the binding energy. I think this is not a very interesting slide. We will go to the next one. Yeah, here. Now since we are talking about solids, your core electrons here, as you come to valence electrons, it forms this band, right? And then at this band, somewhere here you have Fermi level. Fermi level is the highest level in which electrons are occupied. Beyond that, you may still have energy states, but there are no electrons to fill there. Energy states are there. So you have number of electrons are fixed, right, for each element. So solid also will have fixed number of electrons. So it will fill up to that point, that is EF. That is EF. Okay. And that is the work function. Now work function, you remove the electron from here, it will go to somewhere here, vacuum level. Vacuum level means level at which the electron is sitting without any influence from the solid. Vacuum level, there is no level there, it is only the imaginary thing that you remove the electron from the surface to the extent where it doesn't get influenced by the surface. Okay. So you need to have this Fermi level, and that is vacuum level. The difference is work function. The difference is work function. Okay. Difference is work function. Now the excited atom, once you remove the electron, I said this is very unstable. So it takes two paths. One path is that it can again give out X-rays or any other radiation, so that it will its excited state will come down, or other way is releasing the Auger electron. That's what Auger process. These are the two ways the excited, the photoionized atoms get relaxed. One way, it can give out a photon, mostly in X-ray region, or it can give out a Auger electron. Okay, these are two processes. So now if you see this one here, if the atomic number is smaller, less than 15 or 20, that value is less than 20, you get Auger electron yield. Auger electrons process is more probable. Okay, but if it is but X-ray yield is less. So nuclei which are actually less than 20, roughly around 20, less than 20, you ionize electrons there, right? So the probability of getting Auger electrons is very high compared to X-rays. But if you go to a higher atomic number, then this will come down and X-ray yield will increase. X-ray yield will increase. This is general observation, and people found out this kind of systematics there. Okay, all right. Now, yeah, so this is the summary of it. Auger electron emission also is talking about here. See, this is the remember one thing, To get original electron, you don't need to use only X-rays in photo emission. You can also use another electron beam to knock out the electron and create a core hole. That is also possible. That is also possible. So you remove this, and then you get this electron falls here, and that energy is picked up by this, and then that electron will come out, and you catch it. But the Voyager, generally what happens is Voyager electron, number of Voyager electrons coming out is very low, very small compared to photo electrons. So you have to use special equipment to catch them and then analyze them. Okay, we will not worry much about that. Okay, now I have a solid now. We got some idea what it is now, or should we ask some questions here? Any questions from your side? Good. I also learn from you sometimes, sometimes you ask questions which are difficult.
Sir, how do we make sure that we only excite the core electrons? If we give X-rays, wouldn't the outer shell electrons come out before the core electrons are released?
I didn't catch you correctly. Can you just repeat it once again?
Sir, wouldn't the outer shell electrons come out before the core electrons? How do you make sure that only the core electrons are released when you irradiate it with X-rays?
Acha. So what you are saying is, how do you ensure that core electrons are coming or valence electrons are coming?
Yeah.
That is basically from the by fixing the photon energy. You use X-rays. X-rays can actually have very high energy, so they can go and knock out the electrons with higher binding energy. But they can also remove valence electrons. That is possible in the solid, right?
Yes, sir. That's what I'm asking. So the valence electrons have lower energy, right? So wouldn't they come out before the core electrons?
So that will be reflected in the spectrum. Valence electrons will have lower binding energy, core electrons have higher binding energy. So in the spectrum it will get reflected. If you see here, this is the electronic structure, what we call electronic structure. You must have learned the electronic structure of atoms, 1s, 2s, 2p, etc. Right? Similarly, electronic structure of a metal, for example, of a solid. So these are the core electrons. This is the valence band. This is the EF. That is vacuum level, and then difference is phi, as I mentioned to you. Now, if you use X-ray beam, for example, X-ray beam, you can exactly map this here. See that? Exactly you can map. Like you remove electrons from here, you get a peak here. You remove electron from this, you get peaks here. You remove electrons from here, you get peak there. So you get spectrum like this. So what exactly you see here is translated as a spectrum that you record there. Work function? Okay. Binding energy means, suppose you remove this electron. This electron is sitting in a particular energy level here, right? So you remove this electron, so that means you are the energy required for this electron which is sitting in this energy level has certain energy. That is nothing but your binding energy. See, there is a nucleus here. From the nucleus you have electrons sitting here, electrons sitting in different orbitals, right? So for this electron to sit in this particular orbital has some energy, right? So that energy, if you are removing it, that means you are actually supplying that much of energy to remove that electron. That is the binding energy of the electron. Okay, all right. So this is the binding energy. If you remove this, you supply this much of energy. So that energy is nothing but your binding energy, because the electron is now interacting with the nucleus with certain energy. That is nothing but your binding energy. But then, if you have electron here somewhere in this EF, that is at the top level, and then you remove this electron to this point where there is no interaction, so this energy is your work function. Let me explain to you again. Suppose I have a core electron sitting here. There is an electron, there is a nucleus. This has some binding energy. The energy levels are discrete. No, you must understand that the energy levels are discrete. 1s, 2s, 2p, etc. discrete. So that 1s has certain energy. If electron is sitting there, it is sitting with a particular energy. That is nothing but your binding energy. But in solids, you have all these levels are occupied up to here. That means you have certain number of electrons for each atom, right? So if you make them a solid, then all the electrons will fill up this, and then they stop here. Now when you are ionizing, you start ionizing electrons from here. If this electron is going away from the EF, it goes to all the vacuum level. That means it is not under the influence of the solid, and that energy required, which is called work function.
Just for still Fermi level is the binding energy, and then from there till vacuum level.
No. Not really. See, you are removing electron from this level. This level has some energy. For example, you take hydrogen atom. Has 1s electron. How much energy you spend to remove that electron? 13.6 electron volt. That is binding energy. That's all. But work function is, when you have a solid, work function relates to solid, not single atom, right? So you have up to EF, you have electrons are full. So you are removing electron from EF, and this electron goes away under the, will not be under the influence of the solid where it is ionized. The energy required for that is work function, right? So that energy difference is EF minus vacuum level. That is called vacuum work function. Is that clear now, or is that clear or not? No, you ask. Let us. If it's not clear, tell me. No problem. Okay, that is the hydrogen atom. The hydrogen atom doesn't have work function. Work function is the property of solid. This is an atom. There you have ionization energy. For an atom or a gas phase molecule, you have ionization energy. Equivalent of that in solids is work function.
Sir, in solids you will not have binding
No,
energy?
let me again explain to you. See, if you have atom and molecule, you remove an electron, that energy required is your ionization energy. This is nothing but energy level where your energy of that particular level. But when you go to solid, you still have this ionization energy, but there is nothing but binding energy. Now you call it as a binding energy. There also you can call it as binding energy. So the binding energy is the one which you are talking about. But since there is a EF, the electrons are filled up to that level, and that is the band. It's not a single level. From the top of that, if you remove electron, the electron goes away, right? It is similar to that, Einstein, the photoelectric effect. There you said h nu is equal to phi. H nu is equal to phi means what? That phi is the work function. So the electron has to go away from that. In order to leave the solid, you need to spend that much of energy. That is nothing but your work function, right? In atom, you still spend the energy, but that is ionization energy. You call it the ionization. You don't call it the work function. You don't call it as a work function. Okay? Is that okay?
Yes.
All right. Okay, what do you have here? This is a machine. I think we will skip this one. I have a better one to show you. So here, this you must have seen. This is a Atkins physical chemistry. Gives this picture here. What you have is a lamp. This can be X-ray lamp, X-ray tube, or helium lamp, and it goes, and then you have a sample here, and then that hits the sample, the photons, and then it gives out the electrons, and then some of these electrons pass through this and then come to here. This is a detector. Now here, to catch this electron, you have a hemispherical analyzer. You have one spherical analyzer, another one like this. There is a space here. So the electron passes through that. Okay, right? So you apply positive voltage and negative voltage so that the electron takes this path. Right? This voltage should be such that the electron should take this path. Suppose you vary this voltage across, it can come and hit this or this, so it is lost. So if you are applying a particular voltage, which is similar, which is related to kinetic energy. Yeah, other side negative. So one side it gets attracted, other side it gets repelled. So it will take a particular path. Correct. It is if it doesn't have kinetic energy, it's a different story. Yeah. Sorry. Quadrupole. That is for mass spectrometry.
Make them go stable oscillation. You apply the voltage and then so it will follow that path. So quadrupole you use that. Like make sure it follows that path.
No, quadrupole, generally that is used for ions. This is only electron. So we are not looking at the mass. We are only looking at the kinetic energy of the electron, right? So the purpose of using this is different. So a simple electrostatic analyzer is sufficient to measure the kinetic energy. We are only interested in kinetic energy, nothing else. Kinetic energy, and then how many electrons are coming out with that particular kinetic energy. That gives you the intensity. That gives the intensity. You measure the kinetic energy. Now the graph is, the spectrum should be so you will have something like this. So kinetic energy is measured here by this analyzer and intensity is measured here, detector. So that gives you the spectrum. That gives you the peak. The intensity is related to the number of electrons coming out, and then the kinetic energy, what you measure, is plotted here. So you can actually you can have your binding energy also here. Either the machine will have an option if you want to measure the record the spectrum in kinetic energy or binding energy mode, you can do that. Huh? No, not exactly, no. Okay. So that is a spectrometer. Correct. They are lost. They are lost. They are not allowed to enter into that. They are lost. Okay. For that, there is another. It's not given in this photo. They will put some lens here to filter out other electrons. They put a lens there. That is not. Those details are not given here, right? So they allow only particular energy electrons, right? Okay. And all the electrons, all the other electrons are lost. Okay. Right. So what you are doing is you change this energy. You are not fixing it. See, you are changing that energy, kinetic energy. You are changing. That voltage that you are applying is proportional to kinetic energy. Now you keep on scanning. So you keep on changing the kinetic voltage. Right? So you allow now one type of electrons of particular kinetic energy, then again next one. So you scan the entire thing, you get peaks of different kinetic energies. Correct. Exactly. Sure. Because you wanted to catch that particular electron, no? See, you need to, there are so many electrons, you have to catch the particular, identify the particular electron and then measure its kinetic energy and see where it is coming from. So you vary the voltage. Okay, all right. So this is the spectrometer. Okay, it's a so in this spectrometer, this is the X-ray tube, and then helium lamp. Those things are here, and the entire thing is under vacuum of the order of not equal to, less than -9. It will be about up to 10 to the power of. Nowadays, people are talking about 10 to the power -13 torr. -13 torr. Okay, it is very, very high, very, very low pressure, high vacuum. So this entire thing is under vacuum. This is the analyzer. This is the analyzer, and you have a lot of stuff to manage that. Sorry? Detector is inside. So detector is somewhere, it will be somewhere here inside. Inside, it will be a small thing inside. But the schematic I gave you, no? So this entire thing, whatever you are seeing is under vacuum. Whatever you are seeing, this entire thing is under vacuum of the order of -9 to -13 torr. Okay, all right. So yeah, so this is the control panel. This entire thing is control panel of that machine. It looks like a cockpit, aeroplane cockpit. Yeah, it scares you actually. When I first started operating this machine, I was very scared. It took me 6 months. But you guys can finish it you can learn in one week or 2 weeks. You guys are smart, right? The generation is very smart generation. So you guys can operate it in just 2 weeks. You will start operating. You know the computers now. When we were students, the calculator that you have now, that used to be a computer for us, which used to occupy this room, whole room. That calculator, what you are using now from that room it has come to small now. Similarly, your brains are also very fast now. Your brains are also very, very fast. All right, and we don't know what you guys will do 20, 30, 40 years later. You are all in 15 years old, you are all 17. So we add another 40 years, right? So you will reach my age at that time. I will not be there, but definitely what you guys will do, we don't know. We don't know. You will change the entire world upside down also. We don't know. Either you make your life much better or you screw up your life. Both are possible. Okay. Already we have done a lot of damage. Previous generations, our generation have done a lot of damage. We are trying to control that damage. Right? Okay. All right. Okay. So this is the modern spectrometer. The spectrometer which I saw was in 1975, now 1977, 75, 77, 78. That time this was the spectrometer. The modern spectrometer is this. Okay. Amazing, right? So it was very complicated those days, but now this spectrometer, now nobody does anything, they will put the sample and it will give the spectrum. But those days, you have to insert a sample, lot of work. The whole thing is 1 day's work, insert a sample, do all that, it takes. So now this is a modern one. It is installed last year in ARCI, you know ARCI, right? Research Park, IIT Research Park. So they have bought it in 2022. Okay. What is the cost of it? Crore. Yeah. It is, I think, about 4 to 5 crores. Okay. All right. Yeah. All right. So that is the story. This is also a spectrometer. Listen to this. This is also a spectrometer which was built in a National Chemical Laboratory by one of my colleagues. This is published in Journal of Physical Chemistry 2013. Is that correct? No, not this. There is one more machine which I don't have it, but this is another machine 2013. Now this is also complicated because the one which you have seen is looks very simple, but if you want to do a lot of other things, it is going to be something like this. Huh?
The model name might be
No, this is published here. Okay, and this was 1970 electron spectrometry chemical analysis. This is there is an article here. There is an article here. Then people, so if you go to the literature, there is so much of work is there on this in this area. There is a journal called Electron Spectroscopy, Journal of Electron Spectroscopy and Related Phenomena. This is a journal, Electron Spectroscopy and Related Phenomena. This is a journal also. Okay. All right. So this is, you want to have a little nice picture, some colorful picture. This is your photon source. H nu comes here, and then you have the electrons coming out. As I said, before they enter into this, they are subjected to some lenses here, so that a particular set of electrons will enter into this. So these electrons will go through this, and this is your detector. But those days, detector was something called channel electron detector, something like, it used to be like a coil, and then there is a small cup, and then there is a coil, something like this. It used to look like this. Something like that, it used to look like that. But these days, there is channel electron multiplier has come, there is newer version. Like your cars will change, the different types of cars. So yeah, this is a schematic of all that. I think I already explained to you. Interestingly, these, you have time or should we stop here? Okay, I 1 second, you are stopping me.
Actually, 1 o'clock there will be lunchtime, so they will not be getting the food actually.
Okay. So then I'll just quickly take another 5 minutes is okay? 5 minutes? Then we'll stop all this thing. Okay, this one, instead of using the X-rays in the lab, there is something called synchrotron source, synchrotron, where you get variety of photons. You can pick whatever you want, right? So this is a synchrotron radiation. This facility is there in Indore, in India. This is built by Government of India, has built this source, right? And then here you use only this for the laboratory, but here you can get a lot even in between also, starting from 40 to 22 all the way to up to 1500 electron volts. You get all photons you will get. So you can choose, I want to use 100 electron volt, I want to use 200 electron volts, I want to use 500 electron volts. You can choose whatever photons you want. Okay. Yeah, I think I'll skip all this. This is the vacuum. These are all stuff that the different pumps they use to get the vacuum. I'll skip all this. So I want you to see this Raja Ramanna Center for Advanced Technology Indore. You visit this website. If you want to know more about Synchrotron Radiation Center. Synchrotron Radiation Center. Okay. Raja Ramanna Center for Advanced Technology. So you can have a look at it. This is in Indore. Okay, I'll skip all this, skip all this, skip all this. So skip all this. Okay, let me explain this and then stop. Now, since we said the electron is coming out from a particular level, that has a memory from which element it is coming out. Let us say take this molecule. This molecule has C, oxygen C, This is ethyl trifluoroacetate. Now I have carbons. There are 4 carbons. So if I remove electron, 1s electron I remove from carbon, 1 electron is coming from all 4 carbons. Will it have the same binding energy? Right. So that is called chemical shift. That is called chemical shift, which you must have taught you in NMR. NMR chemical shift is different from XPS chemical shift. So this carbon is surrounded by 3 hydrogens, etc., and this is 2 hydrogens and 1 oxygen. This is surrounded by 2 oxygen. This is surrounded by 3 fluorines. So electron charge is removed from the carbon. So there is a positive charge developed here. As a result, the 1s electron has more binding energy. So that will give you a single peak here. So this is the peak which is related to this carbon, this is related to this carbon, and that is related to that carbon, that is related to that carbon. All 4 carbons have same 1s electron. Since the environment, chemical environment is different, their binding energy is going to change. This is called chemical shift. Okay? Now you tell me, you assign these carbons here. Alpha, beta, gamma. This is a question I set, last week to students here. You want to find, is it correct? Assignment? So this is a delta. The binding energy is increasing like this. With respect to, this is actually taken as a normalization. So this delta is related to this. Do you agree with that? Do you agree with that or not? This one, this delta is this carbon. This carbon is surrounded by 3 fluorines. That means that should have highest binding energy. So that highest binding energy is here. You keep quiet. Others, let others talk. Huh? Right? So this is the example which is already there in the textbooks. Some of you will see it. Okay? And then this is silicon semiconductor is SiO2. SiO2. You see silicon 2p is coming at 99.15, but same silicon 2p in SiO2 is coming at 103. Because Si4 plus, there is Si0. Automatically the 4 plus will influence the binding energy of the 2p. The binding energy will increase. So it's almost like 99 to 103. 4 electron volts difference is there. So what do you learn from that? You can find out the oxidation state of elements. Not only element, oxidation state of element also you will be able to judge. Okay, all right. This is the last slide. After this, I will stop. This is a sample moon dust. Somebody brought moon dust from the moon. Who went to bring that? There are so many people are going to moon now, right? Some of you also will go to moon for a vacation. No, you don't believe that? Definitely some of you will go to moon for a vacation. Already people are actually trying to do that. Now you see the dust here, moon dust is analyzed by photoemission spectroscopy. They found all these peaks. So what do you learn from this? What do you learn from this? The first thing, number 1, moon dust has potassium, silicon, aluminum, magnesium, titanium, sodium, oxygen, everything is there. Number 1. Number 2, you can see calcium to different energy levels are also noticed here. See that? Aluminum 2s, silicon 2p, magnesium 2s, aluminum 2p. So magnesium 2p, magnesium 2s. Different energy levels are also can also be seen here. And then there is this intensity. You see, some of the intensity is less, some of the element intensity is more. You can say, yeah, the content is more, right? So these are the things that you can actually analyze. So using photoemission spectroscopy, what you can do is, number 1, identify the elements, identify the electron, the oxidation state, right, and then so many things can be done. Okay, all right. This example, this I think I'll make it as the last one. This is the gold. So those days when photoelectrons were identified by using a photographic plate, electrons are coming out, put the photographic plate, and it will give you these lines here. How many of you are aware of this photograph, Dabba photo, what is that, cameras, put a reel and then develop it, right? So that kind of experiment they used to do. Today you do that? You don't do that? Because, see, oh my God, the camera is here, photo also comes immediately. See? To get this, we used to spend 10 to 15 days. You take put a reel, click it, right, and then take it to the Photoshop, and then they'll say, you come tomorrow or day after tomorrow. They'll develop it, they'll show the reel, this is okay, then you print it, that will take another 5 days. So the whole thing, by the time you get to this one, will be around 1 week to 10 days or 15 days. But now it is fraction of a second. See the changes that you guys are seeing. I did that printing and all that in the dark room. Okay, I never imagined that, it happens so fast, these things come here. Now this is the interesting thing, same photographic film people were using here. So these are the two lines which you are seeing is nothing but this one, these lines. These lines you are seeing, these lines today we get the spectrum like this, but those are the ones they were seeing there. Right? Now, so these are different lines. This is the modern spectrum. This is the spectrum those days, somewhere in 1930, 1920, 1910, around that time. Now, this is the gold foil. So people have taken out the gold foil and put some dirt on that. This is a gold foil and just put some dirt, put some grease, touch some grease and then touch it. Put it inside the spectrometer and record the spectrum. There is no gold there. There is no gold. The spectrometer is saying it is not a gold sample. It's not a gold sample. But you know it is, you have put gold only. So spectrometer is wrong or you are wrong? So how do we understand this? It is a surface sensitive technique. Only few angstroms you can analyze. That's why the spectrometer says it is not gold. So you have to understand it. Spectrometer is not wrong. You are also not wrong. The understanding is something which has to be improved. Okay? Life is very nice, very complicated, but you need to be patient to understand and do fantastic job, fantastic things in life. Okay? Wish you all the best in your life and your future, in your studies. Okay? I stop from here.